So, hello everyone. Uh, Today I'll be talking about a small project that I did in the past few months regarding using supervised learning for fast optimization on networks. Uh, I'll do some self-advertisement before I start because unnoticed work is as bad as no work. So this is usually my research portfolio. The part of the presentation today is the one highlighted in blue, and I'll be talking about some aspects of doing real-time optimization for power control. In my everyday activities, I do a lot of patenting activity, which is kind of separate but still somehow connected to the research I do. Uh, Got to make money somehow, I guess. And now we talk about cell-free massive MIMO. So the the paradigm of cell-free massive MIMO basically revolves around the idea that you are allowed to connect different base stations, or more precisely access points, to each other. In the work that I have done, you assume that these things are single antenna entities. In a real life deployment, you might assume them to be the distributed unit of a 5G G node B, for example. And by connecting them together, so this connection together is called a front haul. And by doing this, you are allowed to do cooperative signal processing and improve the coverage for users. So the idea here is to give uniform coverage to everyone in the area. The idea was first introduced by Thomas Marzetta, I believe, and basically it removes the need of cell edges. So everyone is served by all base stations at all times. In doing so, you of course face several problems. The key of them are initial access, which I do not handle in this work. There is precoding and power control that I will talk about in this work, and finally UEAP association part of it I'll talk about in this work. But the biggest challenge that I'll talk about is how do you do power control in such a setup where you have multiple multiple access points serving a single user, and you want to do it fast because the time scale for the coherence block is about, let's say, 100 milliseconds. It's a bit difficult to do in these conditions. The traditional way of doing this problem, I'll show you in the next slide, is the second order cone problem. So given the channel coefficients, this is the large scale fading, which changes over a time scale of several transmit time intervals. This only depends on the path loss and shadowing. You want to get the power control coefficients to meet the objective of max min SINR. So basically, you want to maximize the minimum SINR you have in your system. For an illustration, we have assumed the simplest of all precodings, the maximal ratio combined, but you can do something fancy like minimum mean squared error. It all depends on you. Our system will still work here. And you have a constraint of power budget, that is, all access points can only support certain number of users, or basically certain power to all users. Traditionally, this problem, when written down, can be matched to a second order cone problem one by one, and optimal solution is known by using a series of convex problems. But when you try to do it, it takes a long time, and you would basically have different channel states by the time you realize a solution. So we came up with this idea of using a graph-based representation, followed by applying a graph neural network on that representation to come up with powers in a real-time way. First of all, we basically move from the communication graph to something which is called a line graph, where the idea is you replace the edges by nodes. So you take a pair of access point and a user and you make it into a node. This is natural because you basically are concerned with the channel gain between an access point and a user rather than how they are connected. So given the input of this beta, which is the large scale fading coefficient, you want to approach eta, which is the optimal power. And the idea here is to basically use transformers to figure out what neighbors are relevant for you instead of you doing it by hand. And then basically training the graph neural network with a fair amount of examples of the optimal power control. We use the loss function as the MSE loss of the SINR, which is predicted by the GNN, versus the optimal SINR you get by doing a second order cone program. And the advantages are actually the fact that once you train it on a few examples, for example, a few sizes, this thing is independent of the size of the network. You can make your network bigger or smaller. The same GNN works on all of it. It is relatively fast, as I'll show you. And the computational complexity is linear in the terms of number of edges. So even when you have bigger and bigger graphs, you don't really pay a lot of price. So I'll show you what it means in terms of practical times in the next few slides. Compared to the state of the art CNNs that we had back in the day in 2021, this takes much fewer training examples because of a property which is called permutation equivariance, which basically implies that if you change the input in a certain manner, the output changes in the same manner, permutes in the same manner, which allows us to use a much fewer examples to train the network. So this is the description of our training data set. We follow a 3GPP path loss model for urban macro deployment. And we use these 4 graph sizes. So M is the number of access point, K is the number of users. This is the canonical assumption for cell-free massive MIMO that you need to have this kind of setup. And we use about 80,000 samples, so 20,000 in each case of the optimal power that we could obtain using the second order cone proctor. Using this, we trained the network and then we measured the performance loss, which is defined as the SINR from the optimal minus the SINR from the GNN. And we see that the performance loss on the trained scenarios is obviously very good. Otherwise, I wouldn't be presenting the work. And it's less than 1%. So this is fine. The network can be trained to work fine, which is okay. But when you go to different scenarios, the scenarios that the network has never seen before, both in terms of the distribution of the channel, in the sense that if you move from an urban macro deployment to a rural deployment or a urban micro deployment, or you change the size of the graph, that is, you have more access points, more users, less access points, however you want, the network still performs better. So in general, on a huge variety of network sizes and deployments that we tested, we found that you can have like less than 5% of a difference from the optimal solution. But you might ask, then why do we even use it? The answer is you are actually 100 times faster than the optimal solution that you can do with an SoC. And this 100 times improvement in speed basically makes it a candidate to be implemented on the network side, because now you can do it in about 50 milliseconds with a bad implementation that I did, but in about 25 milliseconds with a good implementation. So in a sense, this allows you to do good approximation of an optimal solution and thus make it practical to be deployed on the network side. It generalizes very well to different network sizes, to different channel characteristics. And that is a good candidate for implementing such power control on the network side. These are the references that I have used for the talk. Some of them are our papers, other are the canonical references for the GNN. But in a nutshell, this is what our work is. So given the large scale fading coefficients, you can actually generate the power control coefficients very fast using a clever representation of the network and using a graph neural network on that clever representation. So thank you for your attention. Any questions?
Thanks. I don't think that's on. Thank you. Very interesting. I was wondering your comparison when you compared your GNN against the SOCP. The SOCP is an optimal solution?
Yes, it is optimal.
Did you also compare it against a decent good heuristic or decent good approximation?
We compared it with what is called, the simplest heuristic is an equal power heuristic, where you give everyone an equal power. The performance in terms of the SINR you can achieve by such a heuristic is very bad. So in terms of time, definitely it takes just one operation to do. But in terms of the performance, it is very bad.
And anything in between? I'm sure there are better heuristics.
We tried a bunch of them, but we find that if you want to be in the same. So basically they consider if you do like less than 20% away from the optimal, then people are not very happy with your solution. So if you want to do that, we cannot find another heuristic which is on the same time scale as the GNN solution.
Great, thanks.
Yes. Also, this is a bit explainable because, well, we know how we trained the GNN on, and the representation is rather straightforward. So.
Thank you. Just on the time scale question. So what is the right time scale? Because presumably you have your fading coefficients that are changing. It takes some time to get them updated, takes some time to send them to that central unit.
Yes. So,
I mean, what is the right time scale in order for this to work? Because you need all these things to fall in place, right?
So by the references that I have, the coherence block that I can calculate for a relatively low mobility scenario turns out to be about 100 milliseconds. This is the time you have to send your pilots, obtain the channel information, and then do this power control. Thankfully, you don't have to do this power control every TTI. And also, depending on the deployment scenario, you can assume relatively stable large-scale fading for a few transmit time intervals. In that sense, this solution will hold. So the computation that you can do, this is not done by any means in an efficient manner. You can do a big network in about 50 milliseconds. You have, let's say, about 120 milliseconds in practice to do everything. So.
Thank you.